Welcome back to the Deep Dive, where we unpack the essential insights you need to be truly well informed. Today, we're kicking things off with some ancient wisdom, actually, from the Greek philosopher Heraclitus.
Mm,
Everything changes and nothing stands still.
that's a great starting point.
Right. And you might think, okay, ancient philosopher, what's that got to do with modern software? Well, basically everything.
Yeah.
Because our applications, just like everything else, they're constantly evolving. And here's the kicker. Features change, and your data, well, it almost always has to change right along with them. Our source material, back in Chapter 1, introduced this really powerful idea of evolvability,
Hmm.
the idea that we shouldn't just react to change, but actually design our systems to adapt easily. It's, not just a nice to have, it feels pretty foundational.
Oh, absolutely. And it's not just about rolling out some, shiny new feature. Think about it. The application code itself
Hmm.
and the data formats it uses are in this constant dance of flux.
Right.
And the real world throws some serious curveballs that force old and new versions to coexist, like server-side applications.
Yeah.
You might do a rolling upgrade, right? Deploying new versions bit by bit to avoid downtime.
Okay.
Or think about client-side apps, like on your phone. You're totally at the mercy of your users. They might not update for weeks, maybe months.
Yeah, tell me about it.
So you end up with old code and new code, old data and new data, all potentially bumping into each other, needing to somehow understand each other.
So when we talk about applications evolving, data changing,
Yeah.
the critical piece here sounds like compatibility. But what does that actually mean in this context? Is it like a one-way thing or...
That's a crucial distinction, yeah. We really need to care about two main types. First, there's backward compatibility.
Yeah.
That's where your newer code can successfully read and understand data that was created by an older version. That was generally the easier beast to tame.
Right.
But then there's the trickier one, forward compatibility. This is where your older code needs to be able to read data written by a newer version.
Ah, okay. That sounds harder.
That's where things get really interesting and often, really challenging.
Indeed. So now that we've got a handle on why compatibility is so vital, the next logical step is exploring the tools. How do different data formats stack up when change inevitably comes knocking?
Exactly.
We're going to take a journey through various data encoding formats, see how they handle these schema changes, and then trace the data's path through the critical arteries of modern systems, databases, services, message queues, and see how these compatibility concerns actually play out. Get ready, because this might challenge some assumptions. Okay, before we dive into the nitty-gritty of specific formats, let's zoom out a bit. Let's talk about a really fundamental challenge. How do we bridge the gap between how a computer thinks about data inside and how it, well, shares that data with the outside world? It's actually a surprisingly fragile bridge.
It really is.
Understanding it is key to building resilient systems. When you're working with data inside your program, it's all in memory, right? Represented as objects, structs, lists, arrays, maybe hash tables, stuff like that.
Optimized for the CPU.
Exactly. Super optimized for fast access, often using pointers. But then when you need to write that data to a file or, send it across a network, those in-memory things just won't cut it. Pointers, for instance, they're meaningless to another process, so you
Yeah.
have to transform it, turn it into a self-contained sequence of bytes. It's kind of like taking a complex sculpture that's your in-memory object and flattening it into a blueprint, the byte sequence, that you can then easily ship somewhere else and rebuild or resculpt back into its original form.
And that whole translation process has specific names, converting from that in-memory stuff to a byte sequence. That's called encoding, though you might also hear terms like serialization or marshalling.
Okay, encoding. Got it.
And the reverse process, turning those bytes back into usable in-memory data structures, that's decoding, or sometimes parsing. Deserialization, unmarshalling, lots of terms.
So many terms.
Yeah, and it's worth pointing out the term serialization can be a bit confusing because it pops up in transaction contexts with a totally different meaning, dealing with the order of operations.
Ah, right.
That's why our source material specifically sticks to encoding, just to avoid that clash and keep things clear.
Okay, that makes sense. And that's why this translation, this encoding and decoding, and crucially their compatibility, are absolutely non-negotiable, especially in these big dynamic systems that are always changing.
Constantly changing.
Like we said, old code, old data formats, new data formats, they will coexist. There's just no getting around it in large systems,
Yeah.
which is why ensuring both backward and forward compatibility isn't just like good practice, it's essential. Absolutely essential for keeping things running smoothly, continuously. Without it, you'd face massive downtime for every single upgrade.
which is just not feasible for most modern applications. You simply can't have downtime every time you want to deploy a new version.
Exactly.
So let's start our tour of data encoding formats. Maybe begin with the ones often picked for sheer convenience, but which, well, they come with some pretty significant drawbacks, especially when you think about evolvability. First up, language-specific formats. Think Java's java.io, serializable, or Python's pickle, maybe Ruby's Marshall.
Ah, yeah, I've used Pickle. Super easy.
Exactly. The big pro is obvious. They are incredibly convenient. You write almost no code to just save and restore your in-memory objects.
So it feels like set it and forget it for the developer, right? Just mark something as serializable, the runtime handles it. Sounds like a dream. What's the catch? There's always a catch.
Oh, there's a huge catch, or several actually. While they're okay for maybe very transient, short-lived things inside a single application instance, they're generally a bad idea for anything that needs to persist or cross process boundaries.
Why is that?
Well, for one, they're usually tied to a specific programming language.
Yep.
That makes cross-language integration incredibly difficult, sometimes impossible. You're basically locking yourself into that language for a long time.
Right. No mixing and matching.
And forget about easily integrating with systems from other organizations. But maybe even more importantly, there are major security problems. Decoding arbitrary byte sequences from these formats can actually lead to arbitrary class instantiation.
Wait, really?
Yes.
Yeah.
And potentially even remote code execution if an attacker manages to inject malicious data. It's a surprisingly common attack vector.
Wow, okay. That's serious.
It is. Plus, versioning is often a complete afterthought. They generally neglect forward and backward compatibility,
Yeah.
and they can be inefficient too. Java serialization, for instance, is kind of notorious for bad performance and really bloated encoding size. So yeah, that convenience, it often comes at a really steep price.
Okay, so language-specific formats are basically out for anything serious or long-lived. What about the crowd favorites? You know, the ones everyone uses, even if they grumble about them. JSON, XML, and CSV, what's their deal?
Right, the common trio.
Their big appeal seems to be that they're textural and, supposedly human readable. They're also decent for data interchange between different organizations because just getting everyone to agree on a format often outweighs pure efficiency concerns.
So
JSON especially just exploded in popularity, probably thanks to being simpler than XML and, crucially, having that built-in support in web browsers. But honestly, when I look at a massive JSON file, human readable feels like a bit of a stretch sometimes. Are these formats really as good as we make them out to be?
that's a fair point. While human readable is listed as a pro, it often feels more like machine-friendly text than something genuinely easy for humans to parse, especially at scale.
Yeah.
And there are definitely some subtle problems.
Like what?
Well, take number encoding, for instance. It's ambiguous. JSON doesn't distinguish between integers and floating point numbers, and it doesn't specify any particular precision. This becomes a real headache with large numbers.
Ah, like the Twitter example, with the huge tweet IDs.
Exactly. Our source brings that up. Twitter's 64-bit tweet IDs. JavaScript can't precisely represent integers bigger than 2 to the power of 53.
Right.
So Twitter's API actually has to send those tweet IDs twice in the JSON payload. Once as a number, which JavaScript might mangle, and once as a string, just to work around this limitation.
That's such a classic web developer workaround. Feels so clunky.
It is. Another issue is the lack of direct support for binary strings. If you need to embed binary data, you typically have to encode it using base 64.
Which makes it bigger, right?
Yep, inflates the data size by about 33%, and it's just, well, hacky. And while JSON and XML do have optional schema languages like XML schema and JSON schema, they're often complex and, frankly, frequently not used in practice.
So people just hard code the logic.
Often, yeah. Applications end up hard-coding the logic for interpreting things like numbers or binary strings, which can lead to inconsistencies. And don't even get me started on CSV. It lacks any formal schema, making its interpretation really vague. What happens if a value has a comma or a new line? Parsers often struggle. But despite all these flaws, they remain incredibly popular, especially for that interorganizational data exchange where just having an agreement is the main goal.
Okay, so JSON, XML, CSV, useful but flawed. What about trying to make them binary? I've heard of things like message pack or BSON. Do they fix the problems?
Well, they try. Binary variants of JSON XML, like message pack, BSON, and others, their goal is mainly compactness. And they do achieve some reduction. For our example record, let's see, username Martin, favorite number, 1337 interests, daydreaming, hacking. Message pack encodes that in 66 bytes.
Okay, 66 bytes. How does that compare to plain JSON?
Plain JSON without extra white space is about 81 bytes for the same thing. So message pack saves you about 15 bytes.
Hmm. So you lose the human readability, which was kind of the main selling point of JSON XML, for only a marginal gain in space. Doesn't sound like a fantastic trade-off.
Exactly. The trade-off is often not worth it. You lose readability for a relatively small space saving. And crucially, these binary JSON variants still include the field names, like username, right there in the encoded data. That inherently limits how compact they can ultimately be.
Okay, so we've seen the convenient but flawed and the popular but flawed. What if you really need speed, efficiency, and rock-solid schema evolution? Is there a better way?
Yes, there absolutely is.
This is where it gets really interesting, right? This is where we bring in the heavy hitters. The efficient, schema-driven binary formats like thrift and protocol buffers.
That's right. They are built on a similar core principle. You must have a schema. You define your data structure up front. Thrift uses its interface definition language, IDL. Protocol buffers uses its message syntax.
And in those definitions, you specify field tags, these unique numbers, and the data types.
Exactly. And those field tags, the numbers, are absolutely key. They're like the data's permanent address. It's how the system finds a piece of information, even if you rename the field later or add new fields around it. That makes them incredibly robust for evolution.
And what's cool is they both come with code generation tools, right? You feed them the schema.
Yep, you feed the schema definition to the tool, and it spits out classes or structs in various programming languages, Java, C++, C, Python, whatever you need. Your application then just calls this generated code to handle the encoding and decoding.
So how efficient are they if they don't include field names?
That's the magic. When it comes to the actual encoded data, there are no field names at all, just those compact field tags, the numbers from the schema, and the values.
Okay, so for our example record, the one that was 81 bytes in JSON and 66 in message pack.
Right. Thrift has a couple binary protocols. Its standard binary protocol uses 59 bytes for that record, but its compact protocol gets it down to just 34 bytes.
Wow, 34.
And protocol buffers is very similar, encoding the same data, just 33 bytes.
That's less than half of message pack.
Exactly. They achieve this by packing the field type and tag number into single bytes where possible, using variable length integers for efficiency. It's really quite clever. Much, much more compact than JSON or even binary JSON.
Okay, that field tags are critical and cannot change rule sounds like the absolute golden rule for making these things evolvable. What's the thinking there? Is it basically about forgiveness, like always be forgiving to older versions of data?
That's precisely it. The field tags are the secret sauce for their schema evolution rules. Rule number 1, field tags are critical and cannot change. If you change a tag number, all your existing encoded data becomes invalid because the system can no longer reliably find that field.
That you can change the names.
Yes, field names can change because they aren't actually in the encoded data, only in the schema definition used by the code generator. When you add new fields to your schema, you absolutely must use new, unique tag numbers that haven't been used before. If older code encounters data that contains a tag number it doesn't recognize, because it's from a newer schema, it can simply ignore it. That gives you forward compatibility.
Makes sense. And backward.
Backward compatibility works because new code can always read old data. The tags it knows about still have their original meaning. The crucial caveat here, though, is that new fields cannot be required if you add them after the initial deployment.
Why not?
Because old data won't have that field. If your new code requires it, it will fail when reading old data. So any new fields added later must be optional or have a default value defined in the schema.
Gotcha. And removing fields.
Similar idea. You should only remove fields that are optional.
Yeah.
And importantly, you can never reuse the tag number from a removed field.
Never reuse it.
Never. Because old data encoded with that tag might still exist somewhere, or old code might still expect it. Reusing it would cause chaos. Data type changes are sometimes possible, like changing a 32-bit integer to 64-bit, but they can be risky and might cause truncation or precision loss if you go the other way.
Interesting.
Oh, and protocol buffers has a slightly quirky thing with its repeated marker for lists. It actually allows you to change an optional single-value field to repeated list of values. Old code reading new data just sees the last element of the list.
Huh. What about thrift?
Thrift doesn't allow that. It has a dedicated list data type, so changing between single and list requires adding a new field with a new tag.
Okay, thrift and protocol buffers sound powerful, efficient, and well thought out for evolution using tags. But now, let's switch gears to Avro. You said it's fascinatingly different. How so?
Avro's most distinct feature is it uses no tag numbers. Not in the schema, not in the encoded data.
No tags at all. How can that possibly work?
It sounds counterintuitive, right? But the encoding itself is just the values concatenated together. Our example record, encoded in Avro, takes only 32 bytes. That's the most compact of all the formats we've looked at.
32 bytes. Even smaller than protobuf.
Yep. But the catch is, the encoded data itself contains absolutely nothing to identify fields or their data types. It's just raw values. This means for the data to be decoded correctly, the reader needs the exact same schema the writer used.
Okay, that sounds brittle. How does it support schema evolution then if there are no tags and the schemas have to match exactly?
Yeah, that's the clever part. It doesn't require the exact same schema for evolution. Instead, Avro introduces the concept of a writer's schema, the schema used to encode the data, and a reader's schema, the schema the application currently expects.
Writer schema and reader schema. Okay.
When data is decoded, the Avro library needs both of these schemas. It looks at them side by side and effectively translates the data from the writer's schema structure into the reader's schema structure.
How does it match things up?
It matches fields based on their names. If the writer schema and reader schema have fields with the same name, Avro assumes they mean the same thing, even if they're in a different order.
Okay, matching by name.
Right. If the writer schema included a field that isn't in the reader schema, the reader just ignores it. If the reader schema expects a field that isn't in the writer schema, then the reader fills it in using a default value specified in the reader schema.
Default values seem key here.
Absolutely central.
Hi.
Avro's schema evolution rules revolve around default values. To maintain compatibility when schemas change, you can only add or remove fields that have a default value specified in the schema.
So if I add a field,
If you add a field with the default value, new readers reading old data, which lacks the field, will simply use that default. If you remove a field that had a default value, older readers expecting that field when reading new data, which lacks it, will be given the default value from their older schema.
what about nulls? Can the default just be null?
Interestingly, no, not automatically. If you want a field to be nullable or have null as a default, you have to be explicit in the schema using a union type, like union null string or union null long. This makes you think carefully about nullability, which actually helps prevent bugs.
That's good. And changing types or names.
Changing data types is possible if Avro knows how to convert between them. Changing a field name is also possible and backward compatible if the reader's schema specifies an alias for the old name. But it's not forward compatible? Old readers won't recognize the new name.
But wait a second. If the Avro library needs both the writer schema and the reader schema, how does the reader get the writer schema? You can't put it in the data itself because that would bloat it, right?
Exactly. Sending the whole schema with every tiny record would defeat the purpose. So how the reader finds out the writer's schema depends on the context.
Okay, give me some examples.
Sure. For, say, a large file containing millions of records, like you might have in Hadoop, the writer's schema can just be included once, right at the beginning of the file. Avro has a standard format for this called object container files.
Right, like a header.
Exactly. For databases where records might be written individually over time with different schema versions, you could store a version number with each record. The application reading the record then uses that version number to look up the correct writer's schema from a central database of schema versions.
A schema registry, basically.
Precisely. LinkedIn's Espresso database apparently uses Avro this way. And for network communication, like an Avro RPC, the client and server can negotiate the schema version when they first establish the connection.
So that schema database or registry sounds pretty important for Avro.
It's incredibly valuable, not just for resolving schemas at runtime, but also as living documentation. And you can use it to check compatibility before you deploy changes.
So back to the no tag numbers thing. Why is that important for Avro? What advantage does it give?
This leads to one of Avro's key strengths.
Sure.
It's much friendlier to dynamically generated schemas.
What do you mean by that?
Imagine you want to dump the contents of a relational database into a binary format. With Avro, you can pretty easily write code that connects to the database, inspects its schema, table names, column names, types, and dynamically generates a corresponding Avro schema on the fly. Column names become field names.
Okay.
Now, if the database schema changes later, someone adds a column, you just run your export process again, it generates the new Avro schema automatically, and the Avro evolution rules handle the compatibility using field names and defaults. You don't need to manually assign and track tag numbers for every single database column.
Ah, I see. With thrift or protocol buffers, you'd have to manually edit the .proto or .thrift file and assign a new tag number for that new column.
Exactly. That would likely require manual intervention, which can be error-prone and tedious, especially if you have hundreds of tables or schemas that change often. This dynamic generation wasn't really a design goal for Thrift or Protobuf.
That's a really interesting difference. What about code generation? Thrift and protobuf rely heavily on it.
They do. And that's great for statically typed languages like Java or C#, giving you compile-time type safety and efficient in-memory objects. Avro offers code generation too, and it's useful in static languages. But crucially, Avro can also be used without code generation.
How?
Well, in dynamically typed languages like Python or Ruby, you can often just work with the decoded data directly as generic records or dictionaries. And those Avro object container files we mentioned, they embed the writer's schema, so they're self-describing. Tools that process data, like Apache Pig, can often read these files directly without needing any pre-generated code.
Okay, so after exploring thrift, protocol buffers, and Avro, what's the big takeaway regarding schemas? Are they generally a good thing for binary formats?
Absolutely. Summing up the merits of schemas for these binary formats. First, they enable much more compact encoding by omitting field names. That saves space and bandwidth. Second, the schema itself acts as valuable, machine-readable, and potentially always up-to-date documentation for your data structures. That's huge for collaboration and understanding.
And the compatibility checks.
Crucial. Having a schema, especially in a registry, allows you to check for forward and backward compatibility before you deploy anything. You can catch breaking changes early. For statically typed languages, the code generation from the schema is a major win. Compile time checks, better tooling, less manual coding.
So it offers flexibility, but with more safety nets.
Exactly. You get flexibility somewhat similar to schemaless formats like JSON, but with much better guarantees about data structure and evolution, plus superior tooling. It's worth noting, this isn't a brand new idea. Older systems like ASN.1, which was standardized way back in 1984, used similar concepts with tags and schemas, though it was known for being quite complex. Thrift, Protobuf, and Avro are arguably more developer-friendly iterations.
Right. We spent a lot of time on how data gets packaged up, but like you said, a package just sitting there isn't doing much. Data has to move.
Yeah.
So let's trace its path. Where does this encoding and evolution stuff actually happen in real systems?
Great question. Let's look at 3 common scenarios where data flows and compatibility is critical. First, data flow through databases. Think about writing data to a database. It's kind of like sending a message to your future self,
Huh, I like that.
because the data you write today will inevitably be read by later versions of your application code, maybe even by totally different applications down the line.
Which means?
Which means both backward and forward compatibility are absolutely crucial here, especially because of rolling upgrades. During an upgrade, you'll have some application instances running the new code and others still running the old code, all hitting the same database.
So new code might write something, old code might read it, or vice versa.
Precisely. And here's an important snag we need to highlight again. Imagine old code reads a record written by newer code. The newer code might have added a new field. The old code doesn't understand this field.
Okay.
Now, if that old code updates some other field in the record and writes the whole thing back to the database, it might accidentally lose the new field it didn't understand.
Oh, that's bad.
It could be really bad. The encoding formats themselves, like Protobuf or Avro, do often support preserving unknown fields during decoding and re-encoding. But you need to be careful at the application level to make sure you actually handle that correctly and don't just discard data you don't recognize.
So it requires careful coding.
Yes. And this whole scenario reinforces that critical concept. Data outlives code.
That phrase really sticks. Data outlives code.
It's fundamental. Your database contents, the actual bytes stored on disk, will likely persist for far longer than any single version of your application code. Schema migration, actually rewriting all that historical data to conform to a new schema, is incredibly expensive, risky, and time-consuming.
So databases try to avoid it?
For simple changes, yes, like adding a new column that allows nulls. The database might just change the schema definition and fill in NLL whenever older rows lacking that column are read. It avoids rewriting everything. We mentioned LinkedIn's Espresso using Avro. That's leveraging Avro's schema evolution capabilities directly within the database storage layer.
What about backups or archives?
That's actually a good opportunity. Archival storage, like taking data out for long-term backups or analytics, is often a good time to re-encode data into the latest schema, maybe using something like Avro object container files so you have a consistent format for your archives.
Okay, databases make sense. What's the next data flow scenario?
Next up, data flow through services, REST and RPC. This is all about how different processes communicate over networks, usually in a client-server kind of style.
Right, APIs talking to each other.
Exactly. And when we say web service, we generally mean an API exposed over the network, typically using HTTP as the communication protocol, though not necessarily just for web browsers. There are two main popular approaches here.
REST and SOAP.
You got it. First, REST, which stands for Representational State Transfer. It's not really a strict protocol, more design philosophy built on HTTP principles. It emphasizes using standard HTTP verbs, get, dig, post, put, delete, using URLs to identify resources, and generally uses simpler data formats like JSON.
REST is everywhere now, especially with microservices.
It really is. It's gained huge popularity and works very well for external or public APIs. Tools like OpenAPI, formerly known as Swagger, are often used to describe REST APIs.
And the other one, SOA.
SOP, Simple Object Access Protocol. This is a protocol typically XML-based. It was designed to be independent of HTTP, although it's often used over it. Its defining characteristic, unfortunately, is often complexity.
Yeah, I've heard that. WSDL.
Exactly. It led to this sprawling ecosystem of WS standards, WS security, WS reliable messaging, etc., and relies heavily on WSDL, the web services description language, for defining the service interface, which is primarily designed for automated code generation by tools.
So needs special tools.
Heavily relies on them. And while it's still used in some large enterprises, its complexity and notorious interoperability issues between different vendor implementations meant it's largely fallen out of favor elsewhere compared to REST.
Okay, so REST is popular. But you mentioned RPC earlier. Remote procedure calls. Frameworks like Horba, EJB, DCOM. They tried to make network calls look like local function calls. Why did that run into trouble? It sounds convenient.
It sounds convenient, but the source argues it's fundamentally flawed because it tries to hide the fact that a network request is vastly different from a local function call.
How so? What are the key differences?
Oh, there are many. A local function call is generally predictable. A network request is inherently unreliable. The network can be down, the remote service could be slow or crashed, the request or response could get lost.
Right, stuff happens on the network.
Exactly. With a local call, if it fails, you usually know why. With a network request, if it times out, you often have no idea what happened. Did the request even get there? Did it get processed, but the response got lost?
Timeout ambiguity. Yeah, that's painful.
It is. And if you retry a request because you didn't get a response, you might cause the action to happen twice unless the operation is carefully designed to be idempotent. Local calls don't have that problem.
Good point.
Then there's latency. Local calls are fast and consistent. Network calls are orders of magnitude slower, and the latency can vary wildly. Passing complex objects is easy locally using pointers, but over the network, everything has to be encoded into bytes, which can be inefficient or complex for large object graphs.
And language differences.
Yeah, if the client and server are written in different languages, the RPC framework has to translate data types, which can lead to subtle issues. Remember JavaScript's problems with large numbers in JSON?
Ah, yes, the 64-bit ID problem again.
Right. So the conclusion is, trying to completely hide the network and pretend a remote call is local is misguided. Part of REST's appeal, ironically, is that it doesn't hide the network. It forces you to think about HTTP methods, status codes, latency, and failures.
So is RPC dead then?
Not entirely. New generations of RPC frameworks like Thrift has its own RPC mechanism, Avro has one, and Google's gRPC, which uses protocol buffers, is very popular, are generally more explicit about the network realities. They often use things like futures or promises or streams to handle the asynchronicity and potential failures more gracefully.
So when would you use modern RPC versus REST?
While a custom binary RPC can be more performant than, say, JSON over HTTP, RESTful APIs tend to offer big advantages for public or cross-team APIs. They're easier to test, debug, experiment with using simple tools like curl or a browser. They work across basically any language and benefit from a huge ecosystem of gateways, caches, and tooling. RPC is often a good fit for internal services within an organization where you control both client and server, and performance is paramount.
Okay. And how do these service communications handle evolution? How does compatibility work here?
For service evolution, there's often a simplifying assumption made. Servers usually get updated first and then the clients.
Right, you control the server deployment more easily.
Generally, yes. So this means that requests sent from potentially older clients to newer servers need backward compatibility. The new server code must be able to read old client requests. And responses sent from the newer server back to older clients need forward compatibility. The old client code must be able to tolerate new fields or changes in the response it wasn't expecting.
And the encoding format determines the rules.
Exactly. If you're using Thrift gRPC with protobuf or Avro RPC, their respective schema evolution rules dictate what changes are safe. If you're using SOP, XML schemas have their own evolution rules, which can be subtle. For RESTful APIs often using schemaless JSON, the convention is usually that adding optional request parameters or adding new fields to response objects is considered a backward compatible change.
What if you can't guarantee clients upgrade, like a public API?
That's a major challenge, especially for cross-organizational services or public APIs, where you can't force clients to upgrade. This often leads to services having to maintain multiple versions of the API running side by side. You see this with version numbers in URLs like V1 users and V2 users, or maybe in custom HTTP headers. It can get quite complex to manage over time.
Okay, that makes sense. Databases, services. What's the third data flow pattern?
The third one is message passing data flow. This is sort of a hybrid sitting between RPC and databases in some ways.
How so?
Well, it's like RPC in that it's often used for communication between processes, potentially with low latency requirements. But it's like databases in that it typically uses an intermediary, a message broker or message queue, which stores the message temporarily.
Ah, like RabbitMQ or Kafka.
Exactly. Those are popular open source examples.
Mm.
Using a message broker offers several advantages over direct client-server requests. It acts as a buffer. If the recipient service is down or overloaded, the broker holds the messages until the recipient is ready. This increases reliability.
What is shock absorber for traffic spikes?
Precisely. It also usually handles automatic redelivery of messages if a consumer crashes before fully processing a message. It decouples the sender and receiver. The sender just sends the message to the broker and doesn't need to know the consumer's IP address or port, or even if the consumer is running right now.
That sounds really flexible.
It is. It also easily allows one message to be sent to multiple recipients, publish, subscribe, and the communication is typically one-way and asynchronous. The sender fires off the message and usually doesn't wait for a direct reply.
Okay. And how does encoding fit in?
Message brokers generally don't care about the content of the messages. They just treat them as sequences of bytes. So you can use any encoding format you like, JSON, protobuf, Avro, plaintext, whatever.
But compatibility still matters.
Absolutely. Because the publisher of the message and the consumer of the message are often different services deployed independently. You need compatibility to allow them to evolve without breaking each other. Backward compatibility lets new consumers read old messages. Forward compatibility lets old consumers read, or at least safely ignore parts of, new messages.
Just like with databases and services.
Exactly. And just like with databases, if a consumer reads a message, modifies it, and then republishes it, perhaps to a different topic or queue, it needs to be careful to preserve any unknown fields from the original message to avoid data loss if the original publisher was newer.
Are there other places message passing shows up?
Yeah, it's also integrated into distributed actor frameworks like Akka, Orleans, or Erlang OTP. These frameworks extend the actor model, where computation happens via independent actors sending messages to each other across multiple machines. Even within these integrated frameworks, if you're doing rolling upgrades, you'll have actors running different versions of the code sending messages to each other. So again, forward and backward compatibility of the message encoding is crucial. For instance, Akka defaults to Java serialization, which we know is bad for compatibility, but it can be configured to use something like protocol buffers precisely to enable safe rolling upgrades.
It really all comes back to that encoding choice, doesn't it?
It really does.
Wow. Okay, so what does this all mean? We've taken quite a journey here. We started with that fundamental need for applications and their data to evolve, constantly change. We went through the details of various encoding formats from the easy but flawed language-specific ones, and the ubiquitous but sometimes ambiguous JSON, XML, CSV, all the way to these sophisticated schema-driven binary formats like Thrift, protocol buffers, and Avro.
Each with its own strengths and weaknesses, especially around evolution.
Right. Each has its place, but their differences in how they handle schema changes, how they support compatibility, it's profound.
Absolutely. What's fascinating, I think, is realizing how that choice of encoding isn't just about saving a few bytes here and there.
Yeah.
It deeply impacts the entire architecture and, crucially, the evolvability of your applications.
Yeah, it's not just an implementation detail.
Not at all. Concepts like backward and forward compatibility, especially in the context of rolling upgrades, they aren't just theoretical concerns. They are practical necessities for building resilient systems that can actually operate continuously and adapt to new requirements without constant painful downtime.
And the good news, it sounds like, is that this is achievable. With careful design, understanding these formats and their trade-offs, compatibility, and frequent low-risk deployments are actually within reach. You don't have to fear change.
Exactly.
Yeah.
You can design for change. So,
So as you, our listeners, go about your day, maybe pause and think about this. What hidden complexities might be lurking in the seemingly simple act of saving or sending data in the systems you work with? And how might thinking about your data's future self, that message to your future self, change how you design systems today?